energy stored in an electric field work required to charge a capacitor. Now, this is a diagram, okay, we saw before. Okay. Now we calculate the work required to charge the capacitor. Okay. Now we move the charge okay. Then at some point, the voltage difference is V prime, okay, in the middle. And we move dq prime from battery to this one. So the work we have to do is V prime dV by definition, okay, VQ. Okay. And at V prime, the voltage difference between is equal to Q prime over C. C is the capacity of this parallel plate capacitor. Q prime is the charge there, already there. Because Q prime, you have a V prime, okay? Yeah. And then the total work is the integration of dW. From where to where? The charge from 0 to total Q. This Q equal to, you will see that the Q equal to VC. And we do the integration, you get it. This is equal to half Q squared, this is over C. This is the work we need to charge the capacitor. In other words, where is the energy? The energy is stored in this capacitor, right? So V equal to CV. So we write this one, we get W equal to half Q squared over C or half CV squared. Where is this energy? This energy is stored in the capacitor. This work is stored as a potential energy in the capacitor. So we see if there is a Q on the capacitor, then the electric energy stored in this capacitor is half Q squared over C. Or if the potential difference between the capacitor is V, then we see there is energy stored half CV squared in this capacitor. We visualize the work required to charge capacitor as being stored in the form of electric potential energy, U, in the electric field between the plates. You can recover this energy at will by discharging the capacitor in a circuit. The potential energy of a charged capacitor may be viewed as the store in the electric field between its plates.
When this Leyden jar holds a charge, a potential difference exists between the two plates of the jar. We can alternately ground each of the plates, yet the charge on the jar is still there. The potential difference between the two plates is all that matters, not the absolute potential of either plate.
This large electrostatic generator will be used to demonstrate the basic properties of these capacitors. The generator is first cranked with no capacitors hooked up, and long but weak sparks are seen to jump frequently between the electrodes. Now we'll hook these Leyden jar capacitors between the electrodes of the machine. The sparks are now much more intense, but come much less frequently.